Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Every second, electricity flows silently through wires, machines, transformers, motors, and control panels. It powers our homes, our factories, our hospitals, and our entire modern life. But electricity has one dangerous habit. When something goes wrong, it does not slowly warn us. It can turn violent in milliseconds. A short circuit can produce thousands of amperes of current. A cable can heat red hot. A motor winding can burn. A panel can explode. And an electrical arc can reach temperatures hotter than the surface of the sun. That is why every electrical system needs a guardian. A device that can detect abnormal current, open the circuit, stop the fault, and protect both equipment and human life. That device is called a circuit breaker. In this documentary, we will clearly understand four important circuit breakers: MCB, miniature circuit breaker; MCCB, molded case circuit breaker; ACB, air circuit breaker; VCB, vacuum circuit breaker. We will understand their history, construction, working principle, ratings, applications, differences, advantages, limitations, and how engineers select the correct breaker for the correct job. To understand circuit breakers, we must first go back to the early days of electricity. In the late 1800s and early 1900s, electrical distribution was growing rapidly. Homes, workshops, and factories started using electrical lighting and motors, but protection systems were very basic. The earliest protection device was the fuse. It contains a thin metal wire. When excessive current flows, the wire heats up and melts. This breaks the circuit. The fuse was reliable, but it had one major problem. After every operation, it had to be replaced. In large industries, this was not practical. Engineers needed a device that could perform the same protection function, but could be reset and reused. This need gave birth to the modern circuit breaker. Over time, circuit breakers became more advanced. They were designed not only to open during overload or short circuit, but also to interrupt dangerous electrical arcs safely. Today, circuit breakers are manufactured according to international standards. For example, IEC 60898-1 covers AC air brake circuit breakers for household and similar installations. For industrial low-voltage circuit breakers, IEC 60947-2 applies. Before learning MCB, MCCB, ACB, and VCB, we must understand what they are protecting against. There are mainly two common electrical faults. 1. Overload. 2. Short circuit. Overload means the current is higher than normal, but not extremely high. This may happen when too many loads are connected, or when a motor is mechanically overloaded. The heat generated in a conductor follows the formula. Heat is proportional to I squared R. That means if current doubles, heating becomes 4 times. So overload may look small, but if it continues, it can damage insulation, burn cables, and start fire. Short circuit is more dangerous. It happens when phase touches neutral, or phase touches earth with very low resistance. During short circuit, current rises suddenly to very high values. This high current produces magnetic force, heat, pressure, sound, and arc flash. A circuit breaker must disconnect this fault current very quickly. When a breaker opens, its contacts separate. But current does not stop instantly. Electricity tries to continue flowing through the air gap between the contacts. This creates an electric arc. This arc is extremely hot. It can melt metal contacts, damage insulation, and create pressure inside the breaker. So the real engineering challenge is not only opening the contacts. The real challenge is how to extinguish the arc safely and quickly. Different circuit breakers use different arc extinction methods. MCB and MCCB use arc chutes. ACB uses air as the arc quenching medium. VCB uses vacuum, where arc cannot sustain easily after current zero. This arc control technology is what separates a small breaker from a heavy-duty industrial breaker. The MCB, or miniature circuit breaker. You see MCBs in homes, offices, small shops, lighting panels, and small distribution boards. An MCB protects low-current circuits from overload and short circuit. Typical MCB current ratings include 6 amperes, 10 amperes, 16 amperes, 20 amperes, 25 amperes, 32 amperes, 40 amperes, 63 amperes, and sometimes up to 125 amperes. MCBs for household applications usually have a rated voltage not exceeding 440 volts AC. An MCB has several important parts. 1. Operating handle. This is used to manually switch on or off. 2. Fixed and moving contacts. These contacts carry current during normal operation. 3. Bimetal strip. This protects against overload. 4. Magnetic coil or solenoid. This protects against short circuit. 5. Arc chute. This splits and cools the arc. 6. Trip mechanism. This opens the breaker automatically during fault. As it heats, the strip bends. After a certain time, it bends enough to release the trip mechanism. The contacts open. The circuit is disconnected. During a short circuit, the current rises suddenly. This high current flows through the magnetic coil. The coil produces a strong magnetic field. This magnetic field pulls the trip mechanism instantly. The contacts open very fast. MCBs are available in different tripping characteristics. The common types are B-curve for lighting, C-curve for motors and general loads, and D-curve for high inrush loads like transformers and welding machines. The next breaker is the MCCB, or Molded Case Circuit Breaker. MCCB is the bigger and stronger brother of MCB. It is used in industrial and commercial electrical systems where current is higher and fault levels are more serious. MCCBs are commonly available from around 16 amperes to 1,600 amperes. Common ratings include 100 amperes, 160 amperes, 250 amperes, 400 amperes, 630 amperes, 800 amperes, 1000 amperes, 1250 amperes, and 1600 amperes. Braking capacity can be much higher than MCB. Typical MCCB braking capacities may be 25 kiloamperes, 36 kiloamperes, 50 kiloamperes, 70 kiloamperes, 100 kiloamperes or more, depending on design and manufacturer. This trip unit may be thermomagnetic or electronic. Electronic trip units are more advanced and can provide adjustable protection such as long-time, short-time, instantaneous, and ground fault protection. Now we come to a heavy-duty low-voltage breaker, the ACB, or air circuit breaker. ACB is used for large low-voltage power systems. It is commonly installed as main incomer breaker, bus coupler breaker, generator breaker, transformer secondary breaker, large motor control center incomer, power control center breaker. Typical ACB current ratings include 800 amperes, 1000 amperes, 1250 amperes, 1600 amperes, 2000 amperes, 2500 amperes, 3200 amperes, 4000 amperes, 5000 amperes, 6300 amperes. Braking capacity may be 50 kiloamperes, 65 kiloamperes, 85 kiloamperes, 100 kiloamperes or more. ACBs are usually used at low voltage, such as 415 volts, 440 volts, 690 volts AC. Modern ACBs have microprocessor-based trip units. They can provide LSIG protection, L, long-time protection for overload, S, short-time protection for short circuits with intentional delay, I, instantaneous protection for severe short circuits, G, ground fault protection for earth leakage or ground faults. The VCB, or vacuum circuit breaker, is one of the most important breakers used in modern power distribution. VCBs are commonly used at voltages such as 3.3 kilovolts, 6.6 kilovolts, 11 kilovolts, 22 kilovolts, 33 kilovolts. In vacuum, there are very few gas molecules, so after current reaches zero in an AC circuit, the arc cannot easily reignite. This makes vacuum an excellent arc extinguishing medium. MCB for small circuits, MCCB for industrial feeders, ACB for main incomers, and VCB for medium voltage networks. Every breaker is designed for a specific range of voltage, current, and fault level. When selecting a breaker, many people look only at ampere rating, but the most important safety parameter is braking capacity. Suppose a 1000 kilovolt amperes transformer supplies a 415 volt panel. If fault current is 25 kiloamperes, the breaker must have a braking capacity equal to or greater than that value. Otherwise, it may fail violently. In a good electrical system, breakers should not trip randomly. They must trip selectively. Imagine this system. Main ACB feeds an MCCB panel. The MCCB feeds several MCB circuits. If one small lighting circuit has a fault, only that MCB should trip. The MCCB should remain on. The ACB should remain on. This ensures only the faulty part is isolated. This is called selective coordination or discrimination. Electricity is powerful because it moves silently, but when it fails violently. That is why circuit breakers are among the most important safety devices in electrical engineering. An MCB protects a small home circuit. An MCCB protects industrial feeders. An ACB protects the heart of a low-voltage power system. A VCB protects medium-voltage networks where energy levels are much higher, different sizes, different designs, different arc extinguishing methods. But one common mission: to sense danger, to break the fault, to protect life, machines, and infrastructure. Behind every glowing city and safe home, there is a guardian waiting for the moment electricity goes wrong. That guardian is the circuit breaker. The better we understand circuit breakers, the safer and smarter our electrical systems become.